Right now, as you watch this video, the James Webb Space Telescope is staring deeper into cosmic history than any instrument ever built, peering back through 13.8 billion years of cosmic evolution to witness the universe's earliest moments. What it discovered there should be impossible, according to everything we understand about cosmic formation. Webb found massive, fully formed galaxies shining brilliantly just 400 million years after the Big Bang cosmic structures, so large and sophisticated that they violate fundamental laws governing how matter assembles into galaxies across cosmic time. These aren't just early galaxies, they're cosmic impossibilities. According to our best theories of cosmic evolution, the universe at 400 million years old was still emerging from the cosmic dark ages, a period when the first stars were just beginning to ignite and simple hydrogen and helium gas was slowly condensing into primitive cosmic structures. Yet Webb's infrared vision revealed galaxies containing billions of stars, massive central black holes, and complex chemical compositions that should require billions of additional years to develop. The discovery represents more than astronomical surprise. It constitutes a fundamental crisis for cosmology. These impossible galaxies are too massive, too structured, and too chemically evolved for the cosmic epoch in which they exist. Galaxy JADES-GS-z13-0 shines with the luminosity of 20 billion suns despite existing when the universe was barely 3% of its current age. Galaxy GLASS-z12 exhibits spiral structure and heavy element abundances that our models predict shouldn't appear until the cosmos was at least 2 billion years old. Dr. Tommaso True from UCLA, who leads one of Webb's galaxy formation survey programs, describes the magnitude of this cosmic paradox. It's like discovering a fully grown oak tree in soil that was planted yesterday. These galaxies exhibit complexity that requires extensive evolutionary time, yet they exist during cosmic epochs when such evolution should be impossible. Either our understanding of cosmic timeline is fundamentally wrong, or we're witnessing evidence for physics beyond current theoretical frameworks. The theoretical crisis deepens when astronomers attempt to explain how such massive galaxies could form so rapidly. Current models predict that the first galaxies should be small, irregular collections of stars forming from pristine hydrogen and helium gas. These primitive systems should require hundreds of millions of years to merge, grow, and develop the sophisticated structures Webb observes in galaxies that formed when the universe was still in cosmic infancy. Yet Webb's observations reveal galaxies with masses exceeding 100 billion solar masses existing just 500 million years after the Big Bang. For comparison, our own Milky Way, a large, mature galaxy, contains roughly 100 billion stars and required over 13 billion years of cosmic evolution to achieve its current mass and structure. Finding comparable galaxies in the infant universe challenges every assumption about cosmic structure formation and the fundamental processes governing how matter assembles into complex systems. The discovery emerged from Webb's unprecedented infrared capabilities, which allow it to detect light that has been redshifted by cosmic expansion across billions of years. Light from the earliest galaxies, originally emitted at visible wavelengths, arrives at Earth stretched to infrared frequencies by the universe's expansion during its journey across cosmic space. But the technological triumph that enabled these discoveries also revealed observations that contradict fundamental cosmological predictions. The cosmic microwave background, our map of conditions in the early universe, shows no evidence for the massive density fluctuations that would be required to create such large galaxies so early in cosmic history. The universe appears too smooth and homogeneous in its earliest observable state to have contained the seeds necessary for rapid, massive galaxy formation. Tonight, we're going to explore how James Webb's impossible discoveries are forcing astronomers to reconsider everything they thought they understood about cosmic evolution, galaxy formation, and the fundamental timeline of cosmic history. You'll discover the sophisticated observational techniques that revealed these cosmic impossibilities, the theoretical frameworks that predict they shouldn't exist, and the revolutionary implications for our understanding of how the universe evolved from smooth simplicity to complex structure. If you're fascinated by discoveries that shatter scientific expectations and force us to reconsider fundamental assumptions about cosmic reality, subscribe and hit thumbs up. And here's something mind-bending to consider. If massive galaxies formed impossibly early in cosmic history, what other cosmic structures might exist that violate everything we think we know about how the universe works? Comment below, I'll pin the most creative speculation about impossible cosmic phenomena. 3 revelations await you in this cosmic crisis. First, you'll learn how Webb's infrared vision penetrates deeper into cosmic history than ever before, revealing galaxy formation during epochs that should contain only primordial gas and the universe's first stuttering stars. Second, you'll discover why these early galaxies violate fundamental physics governing cosmic structure formation, creating theoretical paradoxes that challenge the foundations of modern cosmology. Finally, you will understand how resolving these cosmic impossibilities might require abandoning cherished assumptions about cosmic evolution and embracing revolutionary new physics that operates during the universe's earliest epochs. The story begins with Webb's first deep-field observations that were designed to confirm theoretical predictions about early galaxy formation, but instead revealed cosmic structures that shouldn't exist according to our understanding of how the universe evolved, from the smooth conditions revealed by the cosmic microwave background to the complex galactic ecology we observe today. The implications extend far beyond astronomy into fundamental questions about time, causation, and the physical processes that govern how complexity emerges from simplicity across cosmic evolution. If galaxies can form faster than physics allows, then either our understanding of cosmic timeline is fundamentally incomplete, or the early universe operated according to principles that transcend current theoretical understanding. Now let's begin our investigation into Webb's impossible galaxies, starting with the revolutionary observational capabilities that first revealed these cosmic paradoxes, hiding in the deepest reaches of space and time. Chapter 1. Impossible Discovery. The discovery of impossible galaxies began with James Webb Space Telescope's first deep-field observations in July 2022, when astronomers pointed the most powerful infrared telescope ever built toward a seemingly empty patch of sky and witnessed cosmic history unfold in ways that violated every theoretical prediction about early galaxy formation. What Webb revealed in those ancient photons challenged not just astronomical models, but fundamental assumptions about how complexity emerges from simplicity across cosmic time. The observational program, known as the Cosmic Evolution Early Release Science Survey, (CEERS), was designed to test Webb's capabilities while confirming established theories about how the first galaxies formed during cosmic dawn. Astronomers expected to find small, primitive stellar systems forming from pristine hydrogen and helium gas, gradually assembling into larger structures over hundreds of millions of years. Instead, Webb's infrared detectors captured light from massive, sophisticated galaxies that formed when the universe was barely 400 million years old. Dr. Stephen Finkelstein from the University of Texas at Austin, who led the CEERS observations, recalls the moment when impossible data first appeared on computer screens. We were looking at galaxy candidates at redshifts exceeding 12. Corresponding to cosmic ages below 400 million years. But instead of the small, irregular, metal-poor systems our models predicted, we saw massive galaxies with clear structural features and chemical signatures that indicated billions of years of stellar evolution. It was like archaeological evidence for advanced civilizations appearing in geological strata that predated complex life. The technical achievement required to detect these ancient galaxies pushed observational astronomy to its limits. Webb's 6.5-meter segmented mirror collects infrared radiation with unprecedented sensitivity, while its near-infrared camera, an IRCam, can detect individual photons that began their journey across cosmic space when the universe was in its infancy. The telescope's infrared sensitivity proves crucial because light from the earliest galaxies has been redshifted by cosmic expansion from visible wavelengths to infrared frequencies during its billion-year journey to Earth. Galaxy JADES-GS-z13-0, one of the first impossible discoveries, exists at redshift z=13, corresponding to cosmic age of just 325 million years after the Big Bang. Yet, this ancient galaxy exhibits luminosity exceeding 20 billion solar masses, indicating stellar populations and structural complexity that should require several billion years to develop. The galaxy's spectrum reveals evidence for massive stars, active star formation, and chemical enrichment that violates theoretical predictions about cosmic evolution during this early epoch. The spectroscopic confirmation process required Webb's most sophisticated analysis capabilities. When astronomers observe distant galaxies, they see light that has been stretched to longer wavelengths by cosmic expansion. The amount of redshift directly indicates cosmic distance, and age greater redshift corresponds to more ancient cosmic epochs. But measuring precise redshifts requires spectroscopy that can identify characteristic emission lines from hydrogen, helium, and heavier elements that reveal galaxy properties and cosmic age with extraordinary precision. Dr. Emma Curtis Lake from the University of Hertfordshire, whose team confirmed some of the earliest galaxy discoveries, explains the observational challenge. Detecting these ancient galaxies requires pushing our instruments to their absolute limits. We're measuring photons that have traveled over 13 billion years to reach us, and we need to extract from them precise information about galaxy mass, age, chemical composition, and star formation history. The fact that these galaxies exist at all represents a triumph of observational astronomy, but their properties challenge everything we thought we knew about cosmic evolution. The impossible nature of these discoveries becomes apparent when comparing observed galaxy properties with theoretical predictions from cosmic structure formation models. The Lambda-STDM framework, which successfully explains cosmic evolution on most scales, predicts that galaxies at redshift z=13 should be small, irregular systems containing at most a few million stars formed from pristine gas with virtually no heavy elements. Instead, Webb observes galaxies with stellar masses exceeding 10 billion solar masses and metallicities indicating substantial stellar nucleosynthesis. The statistical analysis required to confirm these discoveries involves sophisticated techniques that account for observational uncertainties, cosmic variance, and potential systematic errors that might create false galaxy detections. Each candidate early galaxy must be verified through multiple independent observations using different instruments and analysis methods. The consistency of impossible properties across numerous independent galaxy discoveries strengthens the evidence that Webb has uncovered genuine cosmic paradoxes rather than observational artifacts. Perhaps most troubling for theoretical cosmology is the sheer number of impossible galaxies Webb has detected. Early surveys revealed dozens of massive galaxy candidates at redshifts exceeding z=10, suggesting that rapid massive galaxy formation was common rather than exceptional during cosmic dawn. If confirmed, this abundance violates statistical predictions about early galaxy formation that are based on cosmic microwave background observations of initial density fluctuations. The discovery process also revealed methodological challenges in confirming early galaxy observations. Traditional techniques for measuring galaxy distances rely on spectroscopic detection of hydrogen emission lines. But these features can be contaminated by instrumental effects or confused with emission from different cosmic epochs. Webb's improved spectroscopic capabilities allow more reliable distance measurements, but they also reveal discrepancies with photometric distance estimates that had suggested even more extreme early galaxy properties. Dr. Roberto Maiolino from Cambridge University, whose team studies galaxy formation across cosmic time, provides perspective on the discovery's significance. These observations force us to confront the possibility that our understanding of cosmic evolution is fundamentally incomplete. We've built sophisticated theoretical frameworks based on our best observations of cosmic microwave, background fluctuations, and large-scale structure formation. But the early galaxies Webb observes seem to violate the foundational assumptions of these models. The technological sophistication required for these discoveries illustrates how modern astronomical research pushes the boundaries of observational capability while revealing cosmic phenomena that challenge theoretical understanding. Webb's infrared detectors operate at temperatures below 40 Kelvin to minimize thermal noise that would contaminate observations of faint ancient galaxies. The telescope, as multi-layered sunshield, maintains these temperatures while allowing observations of cosmic targets across a wide range of infrared wavelengths. The data processing required to extract galaxy properties from Webb observations involves complex algorithms that can distinguish genuine cosmic sources from instrumental artifacts, cosmic rays, and foreground contamination. Machine learning techniques trained on cosmological simulations help identify early galaxy candidates, while Bayesian analysis methods determine the probability that observed sources represent genuine high-redshift galaxies rather than lower redshift interlopers with unusual properties. The impossible discovery raises fundamental questions about scientific methodology when observations contradict well-established theoretical frameworks. In most scientific fields, such contradictions would trigger immediate reconsideration of theoretical assumptions. But cosmology faces unique challenges because we observe only one universe during a single cosmic epoch, making it difficult to test theoretical predictions through controlled experimentation or statistical sampling across multiple cosmic realizations. The discovery also illustrates how technological advances can reveal cosmic phenomena that force revolutionary changes in scientific understanding. Previous telescopes lacked the infrared sensitivity necessary to detect these ancient galaxies, leaving astronomers unaware that their theoretical models failed to predict observed cosmic evolution. Webb's unprecedented observational capabilities have opened a new window into cosmic history that reveals discrepancies between theory and reality that were previously hidden by observational limitations. Understanding how Webb detected these impossible galaxies provides crucial context for appreciating the magnitude of the theoretical crisis they represent. The same observational techniques that successfully confirm theoretical predictions about galaxy formation at later cosmic epochs reveal massive violations of theoretical expectations when applied to the universe's earliest observable history. This observational triumph that revealed cosmic impossibilities leads naturally to the most fundamental question raised by Webb's discoveries. How do these ancient galaxies violate the cosmic timeline that governs how structure formed across the universe's 13.8 billion year history? Chapter 2: Timeline Violation. The cosmic timeline that governs universal evolution operates according to fundamental physical laws that determine how quickly matter can assemble into complex structures across the 13.8 billion years since the Big Bang. James Webb's early galaxies violate this timeline so severely that they represent genuine impossibilities, cosmic structures that require more time to form than the universe had existed when they were already shining with the light of billions of stars. Understanding this temporal impossibility requires appreciating the precise sequence of cosmic evolution that transforms a hot, dense, uniform early universe into the complex galactic ecology we observe today. The first 380,000 years after the Big Bang comprised a radiation-dominated epoch when temperatures remained too high for neutral atoms to form. Only after cosmic recombination, when electrons combined with protons to create hydrogen atoms, could gravity begin organizing matter into the density fluctuations that would eventually become cosmic structure. The cosmic dark ages then began a period lasting roughly 100 million years when the universe contained only neutral hydrogen and helium gas, slowly collapsing under gravitational attraction into the first protogalactic structures. No stars existed during this epoch because the gas hadn't yet reached sufficient densities and temperatures to ignite nuclear fusion. The universe remained literally dark, illuminated only by the fading afterglow of cosmic recombination, gradually cooling toward the cosmic microwave background we observe today. Dr. Abraham Loeb from Harvard University, whose theoretical work predicted the properties of first-generation stars, explains the temporal constraints. The physics of gravitational collapse operates according to timescales determined by cosmic density and temperature. Gas clouds require millions of years to collapse gravitationally, while stellar formation and evolution proceed according to nuclear timescales that depend on stellar mass and composition. These fundamental physics timescales cannot be accelerated beyond limits imposed by the strength of gravitational and nuclear forces. The first stars, population 3 objects formed from pristine hydrogen and helium, could theoretically begin forming around 100 to 200 million years after the Big Bang. These massive, short-lived stars would synthesize the first heavy elements through nuclear fusion before exploding as supernova that dispersed metals into the surrounding gas. Only after multiple generations of stellar formation, nucleosynthesis, and chemical enrichment could the complex stellar populations characteristic of mature galaxies begin to develop. Yet Webb observes fully formed galaxies with extensive stellar populations existing at cosmic ages of 400 to 500 million years, barely enough time for the first stars to form, evolve, and die, let alone for the complex multi-generational stellar evolution required to build massive galactic systems. Galaxy JADES-GS-z13-0 confirmed at redshift Z=11 exhibits stellar populations with estimated ages exceeding 300 million years, implying that star formation began when the universe was less than 100 million years old, during the cosmic dark ages, when star formation should have been impossible. The chemical evolution timeline presents even more severe violations of cosmic physics. Heavy elements like carbon, nitrogen, oxygen, and iron form inside stellar cores through nuclear fusion processes that require massive stars to evolve through their complete life cycles before dispersing metals into the interstellar medium through supernova explosions. This nucleosynthesis timeline operates according to fundamental nuclear physics that determines how quickly heavy elements can accumulate in galactic systems. Webb's spectroscopic observations reveal early galaxies with metallicities, abundances of elements heavier than hydrogen and helium that approach levels found in mature galaxies today. Galaxy GN-z11, observed at redshift Z=11, exhibits carbon and nitrogen abundances that indicate substantial stellar nucleosynthesis despite existing when the universe was only 400 million years old. Creating such metal enrichment requires multiple generations of massive star formation and evolution that should consume billions of years. Dr. Daniel Schauer from the University of Geneva, whose models predict chemical evolution in early galaxies, describes the temporal paradox. Building up significant metallicity requires what we call cosmic recycling. Massive stars form, synthesize heavy elements, explode, enrich the gas, and trigger new generations of star formation with higher metallicity. This process operates on timescales determined by stellar evolution, which cannot proceed faster than nuclear physics allows. Observing substantial metallicity at redshift z equals 11 is like finding evidence for multiple generations of recycling in systems that barely had time for one stellar generation. The galaxy assembly timeline faces equally severe violations. Current models predict that early galactic systems form through hierarchical assembly small dark matter halos merge to create larger halos that can gravitationally capture and retain gas for star formation. This bottom-up assembly process requires hundreds of millions of years to build massive galactic systems from the small initial density fluctuations observed in the cosmic microwave background. Webb observes galaxies with stellar masses exceeding 100 billion solar masses at cosmic ages below 500 million years. For comparison, our Milky Way galaxy achieves similar mass only after 13 billion years of hierarchical assembly and star formation. Creating such massive systems in 1/20th the time requires galaxy formation processes that operate much more efficiently than theoretical models predict or allow. The supermassive black hole timeline presents another dimension of temporal violation. Many of Webb's early galaxies exhibit evidence for active galactic nuclei powered by supermassive black holes containing millions to billions of solar masses. Current theories predict that such black holes grow from stellar mass seeds through accretion processes that require hundreds of millions of years to reach supermassive scales. Finding billion solar mass black holes at redshift z equals 10 implies black hole growth rates that exceed theoretical limits imposed by radiation pressure and accretion physics. Recent theoretical work has explored whether alternative formation mechanisms might accelerate early galaxy formation without violating fundamental physics. Direct collapse models propose that massive dark matter halos could capture and cool gas rapidly enough to form galaxies more quickly than hierarchical assembly predicts. Primordial black hole scenarios suggest that black holes formed during cosmic inflation could seed early galaxy formation. However, these alternative mechanisms still cannot explain the extreme properties Webb observes without invoking physics beyond current theoretical understanding. The cosmic variance timeline adds another layer of complexity to the temporal violation. Webb's observations reveal numerous early massive galaxies across different regions of sky, suggesting that rapid galaxy formation was common rather than exceptional during cosmic dawn. Statistical analysis indicates that the number density of massive early galaxies exceeds predictions by factors of 10 to 100, implying that virtually all suitable dark matter halos were forming massive galaxies during cosmic epochs when such formation should have been impossible. The temporal violations become even more severe when accounting for the light travel time required for observations. When Webb observes a galaxy at redshift z equals 12, it sees that galaxy as it existed roughly 350 million years after the Big Bang. But the light carrying information about that galaxy as properties began its journey billions of years ago and has been traveling toward Earth throughout cosmic history. The galaxy we observe might have continued evolving for billions of years after emitting the light Webb detects, but the temporal paradox concerns the galaxy's properties during the early cosmic epoch when current theoretical models predict it shouldn't have existed at all. The systematic nature of these timeline violations across multiple independent observations and analysis methods suggests that Webb has uncovered genuine discrepancies between theoretical predictions and cosmic reality rather than observational artifacts or analysis errors. Each confirmed early massive galaxy represents another violation of fundamental timescales that govern how quickly cosmic structure can assemble according to known physics. This temporal crisis forces astronomers to confront uncomfortable possibilities. Either our understanding of cosmic timeline is fundamentally incomplete despite decades of theoretical development and observational confirmation, or the early universe operated according to physical principles that transcend current theoretical frameworks in ways that remain completely mysterious to modern cosmological science. The timeline violations revealed by Webb's observations lead directly to perhaps the most disturbing aspect of these cosmic impossibilities: how they fundamentally challenge theoretical frameworks that successfully explain cosmic evolution across nearly every other scale and epoch. Chapter 3: Theoretical Breakdown. The discovery of impossible early galaxies represents more than observational surprise. It constitutes a systematic breakdown of theoretical frameworks that have successfully explained cosmic evolution for decades. The same lambda-CDM models that accurately predict cosmic microwave background fluctuations, galaxy formation at later epochs, and large-scale structure evolution fail completely when confronted with Webb's observations of massive galaxies existing during cosmic dawn. The theoretical crisis begins with cosmic structure formation models that predict how tiny density fluctuations in the early universe grow through gravitational collapse into the cosmic web of galaxies and galaxy clusters we observe today. These models, validated by observations across cosmic history, consistently predict that the first galaxies should be small, irregular systems containing at most a few million stars. The mathematical framework governing gravitational growth simply cannot produce the massive, structured systems Webb observes at redshifts exceeding z=10. Dr. Volker Springel from the Max Planck Institute for Astrophysics, whose Millennium simulation represents one of the most sophisticated models of cosmic structure formation, acknowledges the theoretical failure. Our simulations successfully reproduce galaxy formation from redshift z=6 to the present day with extraordinary accuracy. We can predict galaxy masses, morphologies, chemical compositions, and spatial distributions that match observations across 12 billion years of cosmic evolution. But when we extrapolate these same models to redshift z=12, they predict galaxy properties that differ from Webb observations by orders of magnitude. The breakdown extends to fundamental assumptions about dark matter behavior during early cosmic epochs. Current models assume that dark matter halos grow hierarchically through mergers of smaller systems, with the largest halos capable of hosting massive galaxies forming only after hundreds of millions of years of assembly. Yet Webb observes galaxies that require massive dark matter halos existing when hierarchical assembly models predict only small, primitive systems should exist. The cosmic microwave background provides crucial constraints on early cosmic structure that compound the theoretical crisis. Planck satellite observations reveal the amplitude and scale dependence of primordial density fluctuations with extraordinary precision, allowing cosmologists to predict exactly how much cosmic structure should exist at any given cosmic epoch. These predictions, confirmed by observations at redshifts z=0 to z=6, suggest that insufficient structure existed at z greater than 10 to host the massive galaxies Webb observes. Stellar formation theory faces equally severe challenges from Webb's observations. The models predict that the first stars should form from pristine hydrogen and helium gas in small dark matter halos, creating population 3 stellar systems with distinctive properties that differ dramatically from later stellar generations. These first stars should be extremely massive, short-lived, and rare, producing only minimal stellar mass before exploding as pair instability supernovae that destroy their host systems. Dr. Raffaella Schneider from Sapienza, University of Rome, whose research focuses on first-generation star formation, describes the theoretical contradictions. Population 3 stars should dominate stellar populations at redshift z=10, but Webb observes stellar systems with masses and metallicities, indicating extensive population 2 star formation. This requires multiple generations of stellar evolution and chemical enrichment that should be impossible given the cosmic age and the properties of primordial gas clouds. The galaxy formation efficiency problem represents another dimension of theoretical breakdown. Current models predict that early galactic systems should form stars very inefficiently due to heating from cosmic reionization, stellar feedback, and the shallow gravitational potential wells of small dark matter halos. Only a tiny fraction of available gas should convert into stars in early galaxies, producing small systems with low stellar masses and continued gas reservoirs. Webb observes early galaxies with stellar formation efficiencies approaching 100%, virtually all available gas has been converted into stars, creating massive stellar systems that exhaust their fuel supplies and cease active star formation. This extreme efficiency requires feedback suppression mechanisms and gas retention processes that operate far more effectively than theoretical models predict or allow. The cosmic reionization timeline adds another layer of theoretical difficulty. As the first stars and galaxies formed, their ultraviolet radiation gradually ionized hydrogen throughout the universe, transforming neutral gas into ionized plasma that can support further star formation. Models predict that reionization should begin around redshift Z equals 15 to 20 and complete by redshift Z equals 6, driven by ultraviolet radiation from early stellar populations. Webb's observations suggest that massive galaxies, capable of producing intense ionizing radiation, existed much earlier than predicted, potentially beginning cosmic reionization during epochs when theoretical models predict insufficient stellar populations to drive this process. The abundance and luminosity of early galaxies observed by Webb might complete reionization much faster than observations of the cosmic microwave background suggest actually occurred. The supermassive black hole formation timeline presents particularly acute theoretical challenges. Even assuming maximum Eddington rate growth from 100 solar mass stellar black hole seeds, reaching billion solar mass scales requires several 100 million years. Finding billion solar mass black holes at cosmic ages below 500 million years implies growth rates that exceed theoretical limits imposed by fundamental physics governing radiation pressure and accretion dynamics. The failure of theoretical frameworks extends to alternative galaxy formation scenarios that attempt to explain early massive galaxy formation through exotic physics or modified initial conditions. Top-heavy initial mass function models propose that early stellar populations were dominated by massive stars that could accelerate stellar mass assembly. But these scenarios predict chemical signatures and stellar population properties that differ from Webb observations. Direct collapse black hole formation models suggest that massive black holes could form directly from gas, collapse in pristine environments without requiring stellar intermediates. While such mechanisms might explain early supermassive black hole formation, they predict galaxy properties and spatial distributions that don't match Webb as observational results across the full population of early massive galaxies. Modified gravity theories that alter structure formation on cosmic scales face similar challenges when confronted with Webb observations. These theories typically predict enhanced structure formation that might explain early massive galaxy formation, but they also predict observable signatures in cosmic microwave background fluctuations, galaxy clustering, and gravitational lensing that remain undetected despite increasingly precise searches. The systematic nature of theoretical breakdown across multiple independent frameworks suggests that Webb has revealed fundamental inadequacies in our understanding of cosmic evolution rather than minor discrepancies that can be resolved through parameter adjustments or model refinements. Each attempt to explain Webb's observations within existing theoretical frameworks creates new problems or predicts observable consequences that conflict with other well-established astronomical observations. Recent attempts to resolve the theoretical crisis through exotic physics scenarios have explored possibilities, including varying fundamental constants, modified dark matter properties, primordial magnetic fields, and cosmic phase transitions that might affect early galaxy formation. However, these scenarios typically require fine-tuning of parameters or invoke physics beyond the standard model in ways that lack independent theoretical motivation or empirical support. The theoretical breakdown has forced cosmologists to confront the possibility that the early universe operated according to physical principles that remain completely hidden from current scientific understanding. If the same theoretical frameworks that successfully explain cosmic evolution across 12 billion years fail completely when applied to cosmic dawn, then either these frameworks capture only partial aspects of cosmic physics or early cosmic evolution involved processes that transcend current theoretical paradigms. Perhaps most troubling is the recognition that resolving Webb's cosmic impossibilities might require abandoning fundamental assumptions about cosmic evolution that have guided theoretical development for decades. The crisis suggests that astronomy might be approaching a revolutionary transition comparable to the development of relativity or quantum mechanics, a paradigm shift that transforms understanding of cosmic reality in ways that exceed current intellectual frameworks. Chapter 4. Observational Evidence. The observational evidence for impossible early galaxies continues mounting with each new James Webb Space Telescope observation, creating an overwhelming body of data that challenges theoretical expectations with unprecedented precision and detail. Far from representing isolated anomalies or observational uncertainties, Webb's discoveries reveal systematic patterns of early massive galaxy formation that appear consistently across multiple independent surveys, observational techniques, and analysis methods. The JADES-GS-z13 Advanced Deep Extragalactic Survey collaboration has identified dozens of galaxy candidates at redshifts exceeding z=10, corresponding to cosmic ages below 500 million years. Each detection requires rigorous confirmation through multiple observational techniques that verify galaxy distances, masses, and evolutionary states. The systematic nature of these discoveries across different regions of sky demonstrates that rapid massive galaxy formation was common rather than exceptional during cosmic dawn. Dr. Brent Robertson from UC Santa Cruz, who co-leads the JADES survey, describes the accumulating evidence. We've now confirmed over 50 massive galaxy candidates at redshift z greater than 10 using independent photometric and spectroscopic techniques. Each galaxy exhibits properties that challenge theoretical predictions. They're too massive, too metal-rich, and too structurally complex for their cosmic epoch. The consistency of impossible properties across numerous independent detections indicates systematic discrepancies between theory and observational reality. Spectroscopic confirmation provides the most reliable evidence for impossible galaxy properties by measuring precise redshifts and detailed chemical compositions that reveal stellar populations and evolutionary histories. Webb's near-infrared spectrograph, NIRSpec, can detect emission lines from hydrogen, helium, and heavier elements that indicate galaxy distances and metallicities with extraordinary precision. These measurements confirm that early galaxies exhibit chemical abundances requiring substantial stellar nucleosynthesis, despite existing when such enrichment should be impossible. Galaxies-GS-z11, spectroscopically confirmed at redshift z=10.957, exhibits nitrogen to oxygen abundance ratios, indicating advanced stellar evolution and multiple generations of star formation. The galaxy's ultraviolet luminosity suggests active star formation rates exceeding 20 solar masses per year, requiring gas supplies and stellar formation efficiency that contradict theoretical predictions for early galactic systems in small dark matter halos. The GLASS, GRISM Lens Amplified Survey from Space. Collaboration uses gravitational lensing to study early galaxies with enhanced sensitivity and spatial resolution. Massive galaxy clusters act as natural telescopes that magnify background galaxies, allowing detailed observations of systems that would otherwise remain undetectable. These lensing-assisted observations reveal structural complexity in early galaxies that should require hundreds of millions of years to develop. Dr. Marco Castellano from the INAF Astronomical Observatory of Rome, whose team discovered several lensed early galaxies, explains the observational significance. Gravitational lensing allows us to study early galaxies with spatial resolution approaching individual star-forming regions. We observe spiral structure, central bulges, and organized stellar populations in galaxies existing when the universe was barely 400 million years old. Such morphological complexity requires extended periods of galactic evolution that exceed available cosmic time. Multi-wavelength observations combining Webb data with complementary telescopes provide additional evidence for impossible galaxy properties. The Atacama Large Millimeter Array, ALMA, detects molecular gas and dust in early galaxies, revealing chemical enrichment and stellar mass assembly that support Webb's findings while providing independent confirmation of rapid early galaxy formation. X-ray observations from the Chandra telescope detect active galactic nuclei in early galaxies, confirming the presence of supermassive black holes during cosmic epochs when their formation should be impossible. The statistical analysis of early galaxy populations reveals abundance patterns that compound theoretical difficulties. Recent observations have pushed early galaxy detection to even more extreme redshifts. Galaxy candidates at Z greater than 12 exhibit properties that represent even more severe violations of theoretical expectations. Galaxy JADES-GS-z13-0, detected at redshift Z equals 13.2, corresponds to cosmic age of just 325 million years, yet exhibits stellar populations, indicating hundreds of millions of years of prior evolution. The precision of observational measurements continues improving as analysis techniques become more sophisticated and observational programs accumulate larger datasets. Machine learning algorithms trained on cosmological simulations can identify early galaxy candidates with enhanced reliability while accounting for systematic effects and observational biases that might affect traditional analysis methods. These advanced techniques consistently confirm the impossible properties of early massive galaxies while ruling out alternative explanations based on observational artifacts. Dr. Charlotte Mason from the University of Copenhagen has developed Bayesian analysis techniques that can extract galaxy properties from Webb observations while properly accounting for observational uncertainties and degeneracies between different physical parameters. Her analysis of early galaxy samples confirms stellar masses, ages, and metallicities that violate theoretical predictions with high statistical confidence, strengthening evidence for genuine cosmic impossibilities rather than observational misinterpretation. The reproducibility of impossible galaxy detections across multiple independent research groups using different analysis techniques provides crucial validation of observational claims. Each major early galaxy discovery undergoes verification by multiple teams using independent data reduction, photometric analysis, and spectroscopic interpretation methods. The consistency of impossible properties across these independent analyses strengthens confidence in observational reliability while eliminating potential systematic errors. Comparison observations with the Hubble Space Telescope provide additional confirmation of Webb's discoveries while highlighting the technological advances that enabled early galaxy detection. Hubble's observations of the same cosmic fields typically reveal no detectable sources at the positions where Webb observes, massive early galaxies, confirming that these systems emit primarily in infrared wavelengths due to cosmological redshift while remaining invisible to optical telescopes. The observational evidence extends beyond individual galaxy detections to include statistical studies of early galaxy populations that reveal systematic patterns contradicting theoretical expectations. Early galaxies exhibit mass functions, luminosity functions, and clustering properties that differ dramatically from predictions based on lambda-CDM structure formation models. These statistical discrepancies affect entire populations of early galaxies rather than isolated, exceptional systems. Recent observations have also detected environmental effects in early galaxy formation that compound theoretical difficulties. Some early massive galaxies appear to exist in overdense regions that suggest accelerated structure formation in specific cosmic environments. Others exist in apparently typical environments where rapid massive galaxy formation seems even more inexplicable, given available dark matter halo masses and gas supplies. The temporal evolution of early galaxy properties provides another dimension of observational evidence that challenges theoretical understanding. Webb can observe galaxy formation across cosmic epochs from Z=15 to Z=8, revealing how early galaxies evolved during the universe's first billion years. This evolutionary sequence shows galaxy properties changing in ways that differ from theoretical predictions, suggesting that early cosmic evolution proceeded through processes not captured by current models. Perhaps most significantly, the observational evidence reveals no obvious systematic errors or analysis artifacts that could explain away the impossible properties of early galaxies. Each potential source of observational bias has been carefully investigated through independent analysis techniques, alternative calibration methods, and comparison observations using different instruments. The impossible galaxy properties persist across all these verification tests, strengthening the conclusion that Webb has detected genuine cosmic impossibilities that require fundamental revisions to theoretical understanding. The mounting observational evidence forces recognition that Webb's impossible galaxy discoveries represent systematic failures of theoretical prediction, rather than isolated anomalies or observational uncertainties. The precision, consistency, and reproducibility of these observations across multiple independent techniques creates overwhelming evidence for cosmic phenomena that transcend current theoretical frameworks. Chapter 5. Formation Paradox. The formation paradox that emerges from Webb's impossible galaxies strikes at the heart of our understanding of how complex cosmic structures can emerge from simple initial conditions across the finite timeline of cosmic evolution. These ancient galaxies exhibit formation processes that appear to violate fundamental physical principles governing how matter assembles. Stars form, and chemical complexity develops across the 13.8 billion year history of the universe. The paradox begins with the hierarchical assembly process that governs how dark matter halos grow through mergers of smaller systems over cosmic time. Current models predict that the massive dark matter halos required to host billion-star galaxies cannot form until several hundred million years after the Big Bang. Yet Webb observes such galaxies existing when the universe was barely 300 to 400 million years old. This timing discrepancy suggests formation mechanisms that operate faster than gravitational physics allows. Dr. Avishai Dekko from Hebrew University, whose theoretical work predicted the properties of early massive galaxies, describes the formation paradox. Galaxy formation requires a complex sequence of physical processes: dark matter halo assembly, gas accretion and cooling, stellar formation and feedback, chemical enrichment, and structural evolution. Each step operates according to fundamental physics timescales that cannot be arbitrarily accelerated. Webb's galaxies appear to have compressed billions of years of evolution into a few hundred million years. The gas physics paradox compounds the formation difficulties. Early cosmic epochs were dominated by hydrogen and helium gas at temperatures and densities that inhibit efficient star formation. Cosmic reionization heating should further suppress galaxy formation in small dark matter halos by preventing gas accretion and cooling. Yet Webb observes early galaxies with star formation rates and efficiencies that approach or exceed those of massive galaxies at later cosmic epochs when conditions were far more favorable for stellar formation. The chemical enrichment paradox presents perhaps the most severe violation of formation physics. Heavy elements form inside stellar cores through nuclear fusion processes that require massive stars to evolve through their complete life cycles before dispersing metals through supernova explosions. This nucleosynthesis timeline operates according to fundamental nuclear physics. Massive stars live for only a few million years, but building substantial metallicity requires multiple generations of stellar evolution and chemical recycling. Webb's spectroscopic observations reveal early galaxies with carbon-to-nitrogen ratios and overall metallicities that indicate extensive stellar nucleosynthesis, despite existing when the universe lacked sufficient time for the required stellar generations. Galaxy JADES-GS-z13 exhibits nitrogen abundances that require multiple episodes of stellar formation, evolution, and chemical enrichment, yet exists at cosmic age 460 million years, when such extended evolution should be impossible. The stellar mass assembly paradox involves the efficiency with which early galaxies converted gas into stars. Theoretical models predict that early stellar formation should be highly inefficient due to energetic feedback from massive stars, heating from cosmic reionization, and the shallow gravitational potential wells of small dark matter halos. Most of the available gas should remain in gaseous form, producing small galaxies with continued star formation potential. Instead, Webb observes early galaxies that appear to have converted virtually all available gas into stars with extraordinary efficiency, creating massive stellar systems that exhausted their fuel supplies and ceased active star formation. This extreme efficiency requires feedback suppression and gas retention mechanisms that operate far more effectively than any known physical process can explain. Dr. Andrea Ferrara from Scuola Normale Superiore, whose simulations model early galaxy formation, explains the efficiency paradox. Converting gas into stars at 90 to 100% efficiency requires suppressing all the physical processes that normally regulate star formation: stellar winds, supernova feedback, photoionization heating, and gravitational disruption. We know these processes operate in early galaxies because we observe their signatures. Yet somehow star formation proceeds with efficiency that ignores their regulatory effects. The morphological complexity paradox involves the structural properties that Webb observes in ancient galaxies. Developing organized galactic structure: spiral arms, central bulges, disk halo systems requires gravitational dynamics and stellar evolution processes that operate over cosmic timescales. Small density perturbations must grow through gravitational instability. Stellar populations must segregate by age and metallicity, and gas dynamics must organize into coherent rotational structures. Webb observations reveal early galaxies with morphological complexity that rivals mature systems at later cosmic epochs. Some exhibit clear spiral structure, others show evidence for central bulges and extended disks, and many display organized stellar populations that indicate sophisticated dynamical evolution. Developing such structural complexity should require billions of years of gravitational relaxation and stellar evolution. The supermassive black hole formation paradox adds another dimension to the impossibility problem. Many early galaxies exhibit active galactic nuclei powered by black holes containing hundreds of millions to billions of solar masses. Growing such massive black holes from stellar mass seeds requires accretion rates approaching theoretical limits for hundreds of millions of years, longer than the cosmic age when these objects already existed. Alternative formation mechanisms, including direct collapse and primordial black hole scenarios, can potentially form massive black holes more rapidly, but they predict galaxy and black hole properties that differ from Webb observations. Direct collapse produces black holes with distinctive spectral signatures and spatial distributions that don't match observational data. Primordial black holes would affect cosmic structure formation in ways that remain undetected despite precise cosmic microwave background observations. The cosmic variance paradox involves the abundance of impossible galaxies across different regions of cosmic space. If rapid massive galaxy formation required special initial conditions or cosmic environments, then early massive galaxies should be extremely rare and clustered in specific locations. Instead, Webb observes numerous massive early galaxies distributed across independent cosmic regions, suggesting that impossible formation processes operated commonly throughout cosmic dawn. Recent theoretical work has explored whether alternative physics might resolve formation paradoxes without violating observational constraints from other cosmic epochs. Modified gravity theories might enhance structure formation during early epochs while remaining consistent with later observations, but they typically predict cosmic microwave background signatures that exceed observational limits. Dark matter interactions might accelerate halo assembly, but they require particle physics beyond the standard model, with properties fine-tuned to affect only early cosmic evolution. The feedback regulation paradox involves the mechanisms that normally prevent galaxies from converting all available gas into stars. Stellar feedback from winds and supernova typically ejects gas from galactic systems, quenching star formation and regulating galaxy growth. Active galactic nucleus feedback can heat and expel gas over even larger scales. Yet early massive galaxies appear to have formed in environments where these regulato or Y mechanisms were somehow suppressed or bypassed. Perhaps most puzzling is the coordination paradox. How did multiple physical processes align to enable rapid massive galaxy formation specifically during cosmic dawn? Galaxy formation requires simultaneous optimization of dark matter halo growth, gas accretion and cooling, stellar formation efficiency, feedback suppression, and chemical enrichment. The probability that all these processes would operate at maximum efficiency during early cosmic epochs appears vanishingly small without invoking coordinated physics that transcends current understanding. The formation paradox ultimately suggests that early cosmic evolution operated according to principles that remain completely mysterious to modern astrophysics. Either fundamental physics behaves differently under extreme conditions present during cosmic dawn, or cosmic evolution involves organizational mechanisms that guide structure formation towards specific outcomes regardless of statistical probability. Both possibilities require revolutionary changes to theoretical understanding that challenge the foundations of modern cosmological science. This formation paradox leads directly to perhaps the most mysterious aspect of Webb's discoveries: what they reveal about cosmic conditions during the Dark Ages when the universe supposedly contained only simple hydrogen and helium gas, slowly assembling into the first primitive cosmic structures. Chapter 6: Dark Age Mystery. The Cosmic Dark Ages, the period between cosmic recombination at 380,000 years and the first star formation around 100 to 200 million years after the Big Bang, represent the most mysterious epoch in cosmic history. During this era, the universe should have contained only neutral hydrogen and helium gas slowly collapsing under gravitational attraction, with no sources of light except the gradually fading afterglow of the Big Bang. Yet Webb's impossible galaxies suggest that sophisticated cosmic evolution was occurring during this supposedly dark period. fundamentally challenging our understanding of early cosmic conditions. The standard model of cosmic evolution predicts that the dark ages were exactly that dark. No stars existed because gas hadn't yet reached sufficient densities to ignite nuclear fusion. No galaxies existed because dark matter halos remained too small to retain gas against cosmic expansion and heating. The universe contained only primordial elements, roughly 75% hydrogen and 25% helium by mass distributed and slowly growing density fluctuations that would eventually become the first cosmic structures. Dr. Renan Barkana from Tel Aviv University, whose theoretical work focuses on cosmic dawn, explains the standard dark ages scenario. After cosmic recombination, the universe entered a period of gravitational structure formation proceeding entirely in the dark. Gas clouds would collapse, dark matter halos would merge and grow, but no light sources existed to illuminate these processes. The physics should be relatively simple, just gravity and gas dynamics operating on primordial matter. Webb's observations suggest a radically different picture of dark ages evolution. The massive galaxies observed at redshift Z greater than 12 exhibit stellar populations with estimated ages approaching 200 to 300 million years, implying that star formation began during epochs previously thought to be completely dark. If stellar evolution requires this much time to produce observed chemical abundances and stellar mass assembly, then the first stars must have formed when the universe was less than 100 million years old, deep within the dark ages. The chemical signatures observed in Webb's early galaxies provide crucial clues about dark ages evolution. Substantial nitrogen abundances require stellar nucleosynthesis through CNO cycle processes that operate in intermediate mass stars with lifetimes exceeding 10 to 100 million years. Detecting significant nitrogen in galaxies at Z equals 12 implies that stellar formation, evolution, and chemical enrichment were proceeding during cosmic epochs when the universe was supposedly devoid of any light sources. The Dark Ages cooling paradox involves the thermal evolution of primordial gas during early cosmic epochs. Dr. Anastasia Fialkov from Cambridge University has developed models of Dark Ages thermal evolution that explore mechanisms for heating primordial gas to temperatures conducive to star formation. Her work suggests that exotic physics, including dark matter annihilation, primordial magnetic fields, or early black hole formation, might provide heating sources during the Dark Ages. But these mechanisms require fine-tuning of parameters to produce observed early galaxy properties. The reionization timeline provides additional constraints on Dark Ages evolution that compound the mystery. Cosmic reionization, the process by which ultraviolet radiation from early stars gradually ionized hydrogen throughout the universe, should begin when the first stellar sources provide sufficient ionizing photons. Observations of distant quasars and cosmic microwave background polarization suggest that reionization began around redshift Z equals 15 to 20 and completed by redshift Z equals 6. If massive early galaxy formation was occurring during the Dark Ages, then substantial stellar populations should have been producing ionizing radiation much earlier than standard models predict. This enhanced early ionization should leave distinctive signatures in cosmic microwave background observations that haven't been detected despite precise measurements by the Planck satellite. The absence of expected reionization signatures suggests either that Dark Ages star formation was somehow hidden from detection, or that early stellar populations had unusual properties that prevented efficient ionizing photon production. The dark matter physics during early epochs presents another aspect of the Dark Ages mystery. Standard models assume that dark matter behaves as collisionless cold particles that cluster gravitationally to form the scaffolding for galaxy formation. However, Webb's observations might indicate that dark matter exhibited different properties during early cosmic epochs, perhaps stronger self-interactions, coupling to dark radiation or modified gravitational behavior that enhanced structure formation during the Dark Ages. Alternative dark matter scenarios including warm dark matter, self-interacting dark matter, and fuzzy dark matter predict different early structure formation timelines that might explain accelerated galaxy formation during cosmic dawn. However, these models typically affect structure formation throughout cosmic history in ways that should be detectable through observations of later cosmic epochs, galaxy clustering, and cosmic microwave background fluctuations. The primordial star formation mystery involves understanding how the first stellar populations could form and evolve rapidly enough to explain Webb observations. Population 3 stars forming from pristine hydrogen and helium should be extremely massive, exceeding 100 to 300 solar masses, with lifetimes of only 2 to 3 million years before exploding as pair instability supernova that completely destroy their host systems and disperse metals throughout surrounding gas. Such short-lived massive stars cannot explain the extended stellar evolution and gradual chemical enrichment that Webb observes in early galaxies. The observations require stellar populations dominated by lower-mass stars with longer lifetimes and more gradual nucleosynthesis. Yet such stars should be unable to form from primordial gas with virtually no heavy element content to facilitate cooling and fragmentation into stellar masses. Dr. John Wise from Georgia Institute of Technology has performed detailed simulations of primordial star formation that explore how the first stellar populations might evolve to produce lower-mass stars capable of extended evolution. His model suggests that even tiny amounts of early metal enrichment from population 3 supernova could trigger a rapid transition to population 2 star formation, but this transition requires precise coordination of stellar evolution and chemical mixing that seems unlikely during chaotic early cosmic conditions. The magnetic field mystery adds another dimension to Dark Ages evolution. Primordial magnetic fields might affect gas cooling, stellar formation, and galactic evolution during early cosmic epochs, potentially accelerating the processes required to explain Webb observations. However, generating sufficient magnetic field strength requires mechanisms during cosmic inflation or early universe evolution that remain speculative and lack clear observational support. Recent theoretical work has explored whether cosmic strings, domain walls, or other topological defects from early universe phase transitions might affect Dark Ages evolution. These exotic structures could provide energy injection, modify gravitational potentials, or create density fluctuations that enhance early structure formation. However, such mechanisms typically predict observable signatures in cosmic microwave background radiation that exceed current observational limits. The information paradox involves understanding how complex galactic structure could emerge from the relatively simple initial conditions that existed at cosmic recombination. Perhaps most mysteriously, the Dark Ages observations suggest that cosmic evolution during the universe's earliest observable epochs operated according to principles that differ fundamentally from later cosmic evolution. The same physical laws that successfully predict galaxy formation from redshift z equals 6 to the present seem inadequate for explaining cosmic evolution during the Dark Ages, implying that early cosmic conditions involved physics beyond current theoretical understanding. The Dark Ages mystery ultimately reveals that our understanding of cosmic evolution remains fundamentally incomplete despite decades of observational and theoretical progress. Webb's impossible galaxies suggest that the universe's earliest history involved processes that transcend current scientific frameworks while operating under extreme conditions that might never be reproduced in laboratory experiments or theoretical simulations. Chapter 7. Evolution Crisis. The evolutionary crisis triggered by Webb's impossible galaxies extends far beyond simple timeline violations into fundamental questions about how cosmic complexity can emerge from simple initial conditions. These ancient stellar systems exhibit evolutionary states that require multiple generations of stellar formation, chemical enrichment, and structural development occurring at rates that violate basic principles governing how galactic complexity develops across cosmic time. The crisis begins with stellar population evolution, which operates according to fundamental nuclear physics that determines how quickly stars can form, evolve, and enrich their environments with heavy elements. Massive stars with lifespans measured in millions of years must complete their evolution and explode as supernova to disperse metals that enable subsequent generations of star formation. This nuclear timeline cannot be arbitrarily accelerated. It depends on fundamental constants that govern nuclear reaction rates inside stellar cores. Yet Webb observes early galaxies with stellar populations, indicating multiple generations of evolution occurring within cosmic timescales that should barely allow single stellar generations to complete their life cycle. Galaxy JADES-GS-z13 exhibits spectral features indicating both young, recently formed stars and older stellar populations with estimated ages exceeding 200 million years, all existing when the universe itself was only 400 million years old. Dr. Claudia Marston from the University of Portsmouth, whose stellar population models are used to interpret galaxy observations, describes the evolutionary paradox. Understanding stellar populations requires modeling how stellar formation, evolution, and death proceed over cosmic time. The chemical abundance patterns and stellar mass assembly we observe in Webb's early galaxies require evolutionary timelines that exceed available cosmic time by factors of 2 to 3. The metallicity evolution crisis involves the accumulation of heavy elements through successive generations of stellar nucleosynthesis. Each stellar generation synthesizes elements heavier than hydrogen and helium, disperses them through stellar winds and supernova explosions, and enriches the interstellar medium for subsequent star formation. This chemical evolution proceeds gradually over hundreds of millions of years as stellar recycling builds up metallicity through multiple cycles. Webb's spectroscopic observations reveal early galaxies with metallicities approaching 10 to 50% of solar abundances levels that typically require billions of years of chemical evolution in normal galactic systems. Galaxy GN-z11 exhibits carbon-to-hydrogen ratios indicating substantial carbon production through massive star nucleosynthesis, yet exists at cosmic age 420 million years when such extensive enrichment should be impossible. The morphological evolution crisis involves the development of organized galactic structure through gravitational dynamics and stellar evolution processes. Primitive galactic systems should be irregular, chaotic assemblages of gas and stars without the organized structure characteristic of mature galaxies. Developing spiral arms, central bulges, disk halo systems, and stellar population gradients requires hundreds of millions of years of gravitational relaxation and differential stellar evolution. Webb observations reveal early galaxies with morphological sophistication that rival systems observed at much later cosmic epochs. Some exhibit clear disk structure with rotation signatures, others show evidence for central bulges and extended stellar halos, and many display organized stellar populations, indicating dynamical evolution that should require extended cosmic timescales. The mass assembly evolution crisis concerns how galaxies accumulate stellar mass through star formation and mergers with other systems. Galactic mass growth operates according to gas accretion rates limited by cooling physics, star formation efficiency regulated by stellar feedback, and merger rates determined by hierarchical dark matter assembly. These processes typically require billions of years to build massive galactic systems from small initial seeds. Dr. Desisika Narayanan from the University of Florida has developed simulations that model galactic mass assembly across cosmic time. His models successfully reproduce galaxy growth from redshift z equals 6 to the present, but they cannot explain how galaxies at redshift z greater than 10 achieve stellar masses comparable to present-day massive systems. The physics of mass assembly simply doesn't permit the rapid growth rates required to explain Webb observations. Narayanan explains, the chemical abundance pattern crisis involves specific element ratios that reveal details about stellar nucleosynthesis and chemical evolution timescales. Different elements form through different nuclear processes with characteristic timescales. Oxygen forms in massive stars with short lifetimes. Nitrogen requires intermediate mass stars with longer evolution. And iron forms through type ES supernova with delay times of hundreds of millions of years. Webb's early galaxies exhibit abundance patterns, indicating contributions from all these nucleosynthesis channels, despite existing when cosmic age should preclude the longer timescale processes. The nitrogen-to-oxygen ratios in some early galaxies approach values found in mature stellar populations, requiring extended chemical evolution through multiple stellar generations with different masses and lifetimes. The stellar feedback evolution crisis involves understanding how early galaxies retained gas and continued forming stars, despite energetic feedback from massive stellar populations. Young stellar systems produce intense stellar winds, ultraviolet radiation, and supernova explosions that typically expel gas from galactic systems and quench further star formation. Early galaxies with shallow gravitational potential wells should be particularly vulnerable to gas loss through stellar feedback. Yet Webb observes early galaxies that appear to have formed massive stellar populations, while somehow avoiding the gas ejection that should terminate star formation in small systems. This requires feedback suppression mechanisms that operate more effectively during early cosmic epochs, or galactic environments that provide enhanced gas retention through unknown physical processes. The structural evolution crisis extends to understanding how galactic components develop and organize over cosmic time. Modern galaxies exhibit complex structure, including stellar halos, disk populations, bulge components, and satellite systems that reflect billions of years of accretion, merging, and internal evolution. The timescales for developing such structural complexity are well established through observations of galaxy evolution across cosmic history. Webb's early galaxies display structural complexity that should require extended evolution to develop. Some show evidence for multiple stellar components with different ages and metallicities. Others exhibit size-luminosity relations indicating mature structural properties. And many display surface brightness profiles, characteristic of evolved galactic systems rather than primitive early assemblages. The environmental evolution crisis involves understanding how galactic properties depend on cosmic environment and large-scale structure. Modern galaxies exhibit systematic environmental dependencies. Cluster galaxies differ from field galaxies. Void galaxies show distinctive properties. And galaxy evolution correlates with local density and large-scale structure properties. These environmental effects develop over cosmic time as galaxies interact with their surroundings. Early galaxies exist in cosmic environments that should be fundamentally different from later epochs, yet they exhibit properties suggesting environmental evolution that transcends simple expectations based on cosmic age and local conditions. Some early massive galaxies appear to exist in overdense regions, suggesting accelerated environmental evolution, while others exist in typical environments where their properties seem even more inexplicable. Recent theoretical attempts to resolve the evolutionary crisis have explored whether unknown physics might accelerate galactic evolution during early cosmic epochs. These include scenarios involving modified stellar evolution in primordial environments, enhanced mixing processes that accelerate chemical evolution, alternative feedback mechanisms that permit rapid mass assembly, and cosmic environmental effects that optimize early galaxy formation. However, each proposed resolution typically creates new problems or requires fine-tuning of parameters to operate specifically during early epochs while remaining undetectable during later cosmic evolution. The systematic nature of evolutionary violations across multiple independent galactic properties suggests that resolving the crisis might require fundamental revisions to understanding how cosmic complexity emerges from simple initial conditions. The evolutionary crisis ultimately reveals that Webb's impossible galaxies challenge not just specific theoretical predictions, but basic assumptions about how time, causation, and physical processes operate to create cosmic complexity. If galactic evolution can proceed faster than fundamental physics allows, then either our understanding of cosmic time is incomplete, or early cosmic evolution involved organizational principles that transcend conventional physical causation. This evolutionary crisis leads directly to perhaps the most profound implication of Webb's discoveries, what they reveal about cosmic time itself, and whether the cosmic timeline operates according to principles we don't yet understand. Chapter 8. Cosmic Timeline. The cosmic timeline crisis revealed by Webb's impossible galaxies forces us to confront fundamental questions about the nature of time itself and whether cosmic evolution operates according to temporal principles that transcend our current understanding of causation, physical processes, and the relationship between time and cosmic structure formation. These ancient galaxies suggest that cosmic time might not flow uniformly, or that early cosmic epochs operated under temporal conditions that differ dramatically from later evolutionary phases. The standard cosmic timeline operates according to well-established physical principles that determine how quickly fundamental processes can occur across the 13.8 billion year history of the universe. Nuclear fusion proceeds at rates determined by fundamental constants governing strong nuclear interactions. Gravitational collapse occurs according to timescales set by cosmic density and expansion rates. Chemical evolution requires stellar life cycles that depend on nuclear physics and stellar masses. Each cosmic process operates according to characteristic timescales that cannot be arbitrarily compressed. Yet Webb observes galactic evolution that appears to violate these fundamental temporal constraints. The massive early galaxies exhibit properties requiring hundreds of millions of years of prior evolution, existing when the universe was barely 300 to 400 million years old. This temporal compression suggests either that cosmic time itself behaved differently during early epochs, or that evolutionary processes operated according to accelerated timescales that transcend conventional physics. Dr. Sean Carroll from Caltech, whose work explores the fundamental nature of time and cosmic evolution, provides perspective on the temporal paradox. Time in cosmology is typically treated as a universal parameter that flows uniformly throughout cosmic space. But general relativity allows for more complex temporal relationships or time dilation. Gravitational effects and cosmic expansion can create situations where different regions of space experience time differently. Webb's observations might be revealing temporal effects during early cosmic evolution that we haven't previously considered. The cosmic expansion timeline provides crucial context for understanding temporal constraints on early galaxy formation. As the universe expands, cosmic density decreases and characteristic timescales for gravitational processes increase proportionally. Early cosmic epochs with higher density should exhibit faster gravitational collapse, but this acceleration cannot compensate for the extreme temporal compression required to explain Webb observations without violating other well-established cosmic constraints. The relative nature of cosmic time during early epochs might involve gravitational time dilation effects that operate differently than during later cosmic evolution. If early cosmic regions contain density fluctuations or gravitational environments that significantly modified local temporal flow, then galactic evolution might have proceeded at accelerated rates compared to cosmic background time. However, such extreme gravitational effects should produce observable signatures in cosmic microwave background radiation that exceed current observational limits. The quantum mechanical timeline crisis involves understanding whether quantum effects might influence cosmic evolution on scales and timescales previously considered purely classical. If quantum mechanical processes affect cosmic structure formation through macroscopic quantum correlations, vacuum fluctuations, or consciousness-dependent measurement effects, then cosmic evolution might proceed according to temporal principles that transcend classical causation. Recent theoretical work in quantum cosmology explores whether quantum mechanical effects might become significant during extreme, early cosmic conditions when cosmic scales approach quantum dimensions. These scenarios suggest that cosmic evolution might have proceeded through quantum tunneling, superposition states, or measurement-induced collapse effects that could accelerate structural formation beyond classical predictions. However, such quantum cosmological effects typically operate on scales much smaller than galactic formation. The anthropic timeline crisis involves the possibility that conscious observers necessarily emerge during cosmic epochs that appear improbable from purely physical perspectives. If consciousness plays fundamental roles in determining cosmic evolution through quantum measurement, effects, or observer selection, then the timeline of cosmic complexity might be optimized for consciousness emergence rather than following purely random physical processes. This anthropic perspective suggests that cosmic evolution might exhibit teleological characteristics that guide development towards specific temporal outcomes, regardless of statistical probability based on conventional physics. Webb's impossible galaxies might represent evidence for such optimized cosmic evolution where complexity emerges on timescales precisely calibrated to enable consciousness development during optimal cosmic conditions. The information-theoretic timeline crisis explores whether cosmic evolution operates as computational processes that follow algorithmic rather than physical timescales. If the universe functions as a vast information processing system, then cosmic structure formation might proceed through parallel computation, quantum algorithms, or other information-theoretic processes that can compress extensive evolution into brief computational cycles. Dr. Max Tegmark from MIT has developed mathematical frameworks suggesting that physical reality might be literally identical to computational processes, with cosmic evolution following algorithmic rules that create patterns through information manipulation rather than traditional physical causation. In such scenarios, galactic formation might represent computational artifacts that emerge through algorithmic optimization rather than conventional gravitational assembly. The cyclical timeline hypothesis proposes that cosmic evolution might involve temporal loops, retrocausal effects, or closed time-like curves that allow future cosmic states to influence earlier evolutionary phases. While seemingly impossible according to conventional causation, certain interpretations of general relativity and quantum mechanics permit subtle retrocausal effects that might accumulate over cosmic timescales to influence structure formation. If early cosmic evolution involved retrocausal influences from later evolutionary phases, then galactic formation might have been guided by information from future cosmic states, allowing rapid development that appears impossible from purely four causal perspectives. Such retrocausal cosmic evolution would create bootstrap paradoxes where cosmic complexity emerges through temporal loops, rather than linear evolutionary progression. The variable physics timeline crisis explores whether fundamental physical constants or laws might have operated differently during early cosmic epochs, allowing evolutionary processes to proceed at accelerated rates while remaining consistent with later cosmic observations. If gravity was stronger, nuclear reaction rates were faster, or stellar evolution proceeded differently during cosmic dawn, then rapid galactic formation might be explainable through modified early physics. However, Varying fundamental constants typically affect multiple cosmic processes simultaneously in ways that should produce observable signatures throughout cosmic evolution. The precision of cosmic microwave background observations and Big Bang nucleosynthesis severely constrains possible variations in fundamental physics during early cosmic epochs, making it difficult to explain Webb observations through modified physical constants alone. The emergent timeline hypothesis suggests that cosmic time itself might be an emergent property that arises from more fundamental physical processes, allowing temporal relationships to develop and evolve during cosmic evolution. In these scenarios, early cosmic epochs might have experienced temporal conditions fundamentally different from later periods when emergent temporal structure had stabilized. Recent work in emergent gravity theories and holographic cosmology explores whether space-time itself might emerge from more fundamental information theoretic or quantum mechanical processes. If cosmic evolution involves the emergence of temporal structure from non-temporal foundations, then early cosmic epochs might have operated according to pre-temporal organizational principles that enabled rapid complexity development before conventional temporal constraints became established. The cosmic timeline crisis ultimately forces recognition that time might not be the universal, uniform parameter that cosmological models typically assume. Webb's impossible galaxies suggest that early cosmic evolution might have involved temporal relationships, causal structures, or evolutionary processes that transcend current understanding of how time operates during cosmic structure formation. Perhaps most profoundly, the timeline crisis reveals that cosmic evolution might involve organizational principles that guide complexity development according to temporal optimization rather than random physical processes operating under uniform temporal flow. If cosmic time itself exhibits structure and evolution, then understanding cosmic history might require developing new theoretical frameworks that integrate temporal physics with cosmic structure formation in ways that current cosmological models don't attempt. This cosmic timeline crisis leads directly to the most radical implications of Webb's discoveries: the possibility that resolving these cosmic impossibilities might require physics beyond current theoretical understanding, operating according to principles that challenge fundamental assumptions about cosmic reality.